Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Rass's most distinguishing feature is that he's actually my successor at the University of Wisconsin. So when I left to come to Microsoft, Rass followed me to the University of Wisconsin and then did some great work there and moved to Berkeley and is now doing great work at Berkeley. And Rass is visiting us for 3 days. We'll be here in MSR, so if anybody wants to talk to him, you should get in touch with Rass and make some arrangements to talk with him. So, Rass?
Thank you, Jim. So I haven't been here for a while, which is it's because I didn't feel I have enough stuff that's cool enough to show you, but I think we have now interesting results that are worth presenting here. And what I'll talk about today is our work on synthesis by sketching, which is a project that has 2 efforts in it. And I'll talk about both of these efforts today. And so the talk may take a few minutes over an hour, but the good news is that it only takes 2 slides to give you the key message. The first slide compares sketching with the other 2 traditional approaches for getting software correct and writing it productively. The first is verification, in which you write 2 things. You write a specification of the intended behavior, the functional spec, and then you write also the program, the low-level program, and then verification checks that the specification and the implementation are consistent. There is sort of redundancy there because you first write the spec and then you also implement the program in a lower level language and you check for their consistency. So you're writing 2 things. And this redundancy has been recognized by people who do synthesis. And what they propose is that, well, why don't we just write the spec, ideally declaratively rather than imperatively, and then generate the code that does what we intend. And so if this sounds too good to be true, it's the case. And you, in fact, could say that you fool, didn't they tell you about set L? And in fact, they did tell me about set L. So synthesis is not what we are going to do. But instead, we'll do synthesis with sketching, which is sort of synthesis. The difference is that the spec, at least in our current instance, is executable, which is good because it's easy to debug. And then the programmer sketches the outlines of the desired implementation, sort of to guide the synthesizer, so that the synthesizer doesn't do the dumb, naive thing, but it actually generates code that's good in the way the programmer wants. And so this is what sketching is. The second slide shows the programmer experience with sketching, the intended one at least. So the programmer writes the sketch of the desired implementation, and then the implementation is a completed sketch with all the hairy details. And the synthesizer, of course, doesn't have a basis for knowing what the hairy details should be, so of course there is a spec. And it is this sketching equations in quote that describes the entire effort. And I'll talk about 2 efforts, and the first one sort of follows the vanilla approach in which we'll have a spec, we'll have a sketch, which is the desired implementation, and outline, and then the implementation is provided. So the first effort tries sketching on the domain of bit streaming for crypto programs. And this is an interesting case study because this domain is getting more and more interesting. It spans from crypto to coding to code breaking. And it's interesting because there is a big implementation gap. The difference between the spec and the implementation itself is huge. You can often describe ciphers in a few lines of code because you can do it at the level of bits. But the actual implementation that talks at the level of words, the sort of parallel version of the cipher, is often very different than the spec, or much larger, or both. It's also interesting because in this domain, both performance is critical, obviously, because on servers, up to 95% of cycles can spend time in crypto. Think of encoding pages with SSL. And correctness is, of course, crucial because small mistakes can make it possible to break a large number of keys, as has happened in the past. So the running example that we'll go through this case study is a very simple cipher, if you will. It drops the 3rd bit from every stream. It's hardly a cipher, but it has the properties of other ciphers, surprisingly. It's there is a big implementation gap, as you will see, and there are many different possibilities on how to implement it. It's more like a parity dropping of a bit rather than cipher, but think of it however you like. So there is one way of how to implement this running example, and that's taking 2 bits from a word and compacting it by shifting them. So each of these steps will be probably 3 machine instructions, an AND, and a shift, and an OR. There is a better way, which is logarithmic in the word size, and it's called log shifting. Here we have more parallelism because we shift more bits at once at the cost of shifting some bits multiple times. So it's harder to implement this version of the bit shifting. But in our approach, we can sketch that faster implementation. We start by the functionality, which is what the piece of code should do. It should compact the bits to the beginning of the word, dropping every third. And now the programmer provides the sketch, which visually can be represented like that. What does the sketch say? The sketch says only what the programmer has in mind. The programmer says, it looks like I could implement this functionality, which needs to be decomposed into machine instructions, in 3 steps. In first step, I shift some bits by 1, which is what these question marks say. In the second, some bits by 2. In the third, some bits by 4. And I don't know which bits I need to shift to implement it. And in fact, I don't care whether this implementation strategy works to implement this desired functionality. It doesn't care because the system, the synthesizer, will put these 2 together. And if this strategy can be used, then an implementation will be provided. If the strategy doesn't implement this bit permutation, which may happen if the bits cross, then the system will say, sorry, I cannot help you. And so this is how you avoid bugs in providing a sort of high-performance implementation of your functionality. So for this example, actually, you need 2 sketches. The one that I showed you is this one in the language that we use. Here is another one which shows how to pack bits into words. So the first one talks about bits within words. The second one about bits outside the word. So you don't need to understand it. But this is the program sort of that it generates. But what we want to remember is that compared to having no sketch at all, these 5 lines of a sketch provide significant speed up, a very good implementation, which gets better as the machine gets wider, of course. So to give you an idea, OK, so compare that with 100 plus lines of Fortran, which is actually an existing implementation of a similar benchmark. Another example of what you can do with sketches, more realistic one, comes from the DES cipher. There is a permutation that flips around 64 bits. And you cannot easily implement it, well, efficiently with standard AND and OR operations because there is too much irregularity here. So the programmer needs to do a trial and error to find those implementations. And the one that will sort of work well is using a table. So you take some bits from the input 64 bits, and you index tables, and this is how you do it. Problem is that these tables could be too large, even after this trick. And so what the programmer does, and that's sort of the approach with sketching, that he stares at the permutation and see there is some level of regularity there. And he decomposes the permutation into 2 stages. He sketches the first one, which is very simple. It can be implemented effectively with 1 shift and an OR. And he doesn't specify the second one. The system will synthesize it. And maybe to the programmer's surprise, these permutations here will be now much simpler. They are narrower, 32 bits, and they are identical. So the tables you need to implement them now are 4 times smaller. And therefore, take less space, which makes a big difference on some machines. So I think there are 2 messages on this slide. The first one is that you see that sketches sometimes encode implementation intentions that an optimizer or synthesizer, however you want to call it, would have a hard time finding, except for searching the entire space of possibilities, which seems too large, at least in this domain. Second, you need a trial and error to find a good implementation, and this is the sketch is a convenient way of doing it, because I just state what I want the first stage to do and let the system figure out what the second stage should be, or tell me that the strategy doesn't work, preventing me from introducing a bug.
So by sketching, you mean the programmer actually draws that figure on the left?
No, there actually is a language in standard text syntax in which you state that. So this would be a fragment of it. Effectively, this is the whole thing, which this is the sketch. And the sketch for the second stage is empty, which is to say that the system will synthesize it so that these two permutations together implement the original one.
Synthesize it based on what?
Based on knowing that this is sort of our specification, this is the behavior we want to implement. Now we are looking for a better implementation of this functionality, think of it as a spec. And the better implementation will first do this simple permutation, followed by one that's irregular but smaller. So the system will synthesize the second stage so that these two together implement what you saw before, the 64-bit to 64-bit permutation.
So, how does the programmer know to write the first permutation?
Well, this is where his insight needs to come in. And this is where you need to do trial and error and do it fast, which is why sketching helps. So if you look at it, you see, well, there is some regularity here. And so let me try to do a first stage that's cheap to implement that does that. And maybe something good will come out. Maybe not, you need to come up with a different sketch.
So go back to the previous slide. So, yeah, this one. So the fact that you're not showing us the spec, is there a reason behind that? I mean, is it actually pretty complicated?
No, this is the spec.
No, in text form. In text form.
Well, the spec for this would be one big array which tells you where does this bit land. Or you can imagine
So
various...
it's just
Exactly.
a permutation.
Yes.
Okay.
I could show it to you, but you wouldn't appreciate
sure. Okay.
it.
So you don't have to write it in this.
Exactly.
You're saying it's actually very good.
So these figures here is my programming language for the sake of next 60 minutes. But
So you have to write that program, that sketch program, and you also have to give the spec, right? Which is that table. Whole thing.
that's right. That's right. So you remember that equation, right? You need to have a spec which is the behavioral thing. And then the sketch is sort of outline of the structure of how you actually implement that behavior. And so this is the spec, and now this is the outline of the implementation. This is the completed implementation. Go.
So in this domain, it seems like it's probably impossible for a sketch to kind of defeat the spec. In other words, if I give a spec, there's no way for me to also give a sketch that will somehow mean that no algorithm can be synthesized.
Oh, it is possible.
Oh, it is possible.
Yes, so if you come back here to this one, so this log shifter cannot implement all possible permutations. If some bits crossed here, they could end up at some stage in the same position overwriting each other.
So then what feedback do I get as a programmer if I've done that? What's it look like to me?
We didn't figure that out fully. This is an important part of any sketching system, right? So yeah, that's a research question. So far, we would tell you where bits are overwritten, sort of give you a constraint that cannot be satisfied, but it's far from us being happy with it. Yeah, so feedback is an important thing. So this is the programming experience. So how does it actually all works? And we need to start with the specification, which is the language in which you enter the program. And so it's an executable specification. You can run it. And in the language here in the PowerPoint, it's just that. It takes 3 bits from the input stream, drops the third one. The programmers actually use StreamIt. And this is what this filter looks at it's streaming. In each work cycle, it takes 3 bits, pushes out 2, such that it drops the third one and pushes the first 2. Internally, these filters are represented as matrices, which tell you there are 3 input bits, 2 output bits. And this row tells you that in the first position on the output, there will be the first bit from the input. The semantics is one of matrix multiplication. You take the 3 bits from the input stream, multiply with the matrix, you get a vector that is what you push on the output. Now, we are ready to state the problem of how to do this sketching-based synthesis. You have a spec. Now you have a sketch of the implementation. Now the problem is this. We want to synthesize a program for some target machine that behaves like that, but is implemented structurally like that, somewhere inside. Now even that problem is sort of still fuzzy. So I'll take you to the solution to the problem through several simpler steps. The first step will be having no sketch whatsoever. Now the problem is simply taking the spec and compiling it for the target machine. And the problem is simplified by the observation that any implementation we have in mind over machine instructions such as shifts, ands, and ors corresponds to a data flow program. where each of these filters implement these instructions. So this one is a shift and can be represented with a matrix. And so this is a data flow program that represents the target machine, a target program, a program that you can directly emit into C. We call these programs implementation programs. And so now the baseline compiler, which is one that doesn't accept any sketch, works over a space of these data flow programs. Now some of them are implementations, which is all filters are word size and correspond to machine instructions. These can be directly translated to C. And then there are those that are not in that form, but can be pushed into that form. So if I give you a spec which is not an implementation, I have a bunch of other programs that are functionally identical to it, but structurally different. And these are more decomposed than others, in the sense that we have translated this program through decomposition of filters into a program that contains only machine instructions. And we do it by defining a function, a rewrite function, that takes any program and decomposes it into lower level. And if you apply a sequence of these rewrite rules, you always end up in a program that only contains machine instructions and is sort of rewritable to C. So for that spec, this is the path that the compiler would follow in a greedy fashion to get us an implementation. Not very good, but one that you can run. Trishu.
How do you guarantee termination?
Because the program is always sort of simpler monotonically, and it terminates. Let me show you what these steps are for this domain. Let's assume a 4-bit machine. And here is the filter of our running example. The first step we do, we unroll it so that on the input and on the output it's word size, multiple of a word size. And we split the filter this way so that we obtain 3 filters such that each reads a size of a word. And we split them like that, and we obtain a data flow program where each filter, I didn't split these two, reads in a word and outputs a word. So see, just unroll, chop it like this, chop it like that. Now we have word size filters. These don't correspond to machine instructions yet, but you can decompose it into a filter that is over machine instructions, and you can generate a program out of it. So you see this monotonic decomposition.
Why do you do the horizontal splitting?
Because this is a filter that reads a word, but outputs 2 words.
Oh,
so
okay.
if your instructions operate on word size registers. So you don't need to understand details of what happens here, but you see how you would rewrite it. So this is our simple algebra of rewrite rules that in a greedy way gives you some implementation. And so these are the instructions. Now the second problem that gets us closer to sketching synthesis is one where the programmer provides a fragment of an implementation. So this is not a sketch, right? The programmer specified exactly what these steps should be. There is nothing left ambiguous here. No non-determinism. Now, how does the compiler incorporate this programmer's idea, this log shifting, into the compilation process? Well, in 2 steps. First, the compiler figures out what is the functionality that this implements. And you just collapse it and you realize, oh, this is what the programmer meant. And now in the baseline compilation process, when the compiler encounters a filter that looks like this, that has this functionality, it will be replaced with this pipeline of filters. So there will be a simple rewrite rule guided by the programmer. So here, we decompose, and if at some point there is a filter in the program that looks like this behavior, it will be replaced to what the programmer gave. And so we'll nudge the compiler to go here, and then the greedy translation will follow. So we combine the human insight with what the naive compiler, the baseline compiler, does. And so we only overwrite it when the compiler doesn't do a good job, and we end up with a better implementation. Shivam.
So there's a pattern match that goes on, and all that the user provides is rewrite rules.
That's right.
Then it seems like the user could provide a set of them, and more than one could be applicable. What you're saying seems like a very non-deterministic algorithm.
Yes. So currently, what we have is we need to provide a little bit more than just the rewrite rule. We need to also specify where in that hierarchy of filters, in the hierarchical data flow program, those rules apply. Now, to make it better to avoid the need for specifying where those rewrite rules may and may not apply, we need to do some analysis to guarantee termination. Non-determinism is fine as long as we end up in the same position. But to avoid cycles, we need to do some more analysis, and that's something we haven't done yet.
So I should think of the sketch formally as a set of rewrite rules?
Depends. There are different sketches, and some of them you can think of a set of rewrite rules. Perhaps the best way is to, we'll get to sketch soon, and think then we'll get back to your question. But the fact that, yes, this process could cycle is a problem, and currently we have a solution that could be improved significantly with some analysis that guarantees that we sort of strongly minimize the program.
So before you said you're compiling for a 4-bit machine, right? But the sketch, this rewrite rule you just gave us was on 32 bits?
It was on 16 bits. We'll resolve the problem here. So
you're saying it doesn't have to match?
It actually does have to match.
It does. So I have to actually provide a sketch for 4 bits.
Yes, but that's an easy thing to change since you can have symbolic variables in those. But here is the inconsistency, right? Here is what the baseline compiler would do up to this step. And I'm showing here the process on 4 bits because I wanted to make the matrices manageable. But here I'm showing you this visual language for 16 bits. But pretend that this is 16 bits and all will make sense. So at this point, the programmer provided the sort of recipe, not a sketch. And what happened is that the compiler realized, oh, this filter here actually implements that, and I'm supposed to rewrite it with this. So this will be replaced with a pipeline of 3 filters, and then further rewritten into target machine's instructions. So now we are ready to show how the sketch is incorporated into it. So now the sketch corresponds not to a single filter with a single functionality, but to many different ones, depending on whether you shift the bit or you let it be copied down. And so what happens is, the idea is the same. We go down, and each step we check every filter and see, can it be implemented with the sketch? And if yes, we rewrite it. And so what happens is we again nudge the compiler and overwrite its default naive rule to the one provided by the programmer. And the way you do it is that this is the space of all possible programs that the sketch describes. And from them, we choose one that is functionally identical to this one, to preserve semantics.
How does the programmer know whether their sketch was used in the compilation process?
So right now, we expect that it will be used, and if it's not used, we tell the programmer that we failed to use it. But again, a better diagnostics is needed, and that's part of the research question.
So if you find a solution that doesn't use a sketch, then you go back and try to find another, basically?
Yes. So if you didn't use the sketch, presumably it was because it didn't apply.
Is there any way to know that you're going in the right direction to use the sketch? In other words, or is it just a brute force search?
So usually when the programmer programs with sketches, he understands that what the program looks like at a particular stage of the decomposition. If you look back at this example here, the programmer has an idea of how the program looks like after you split the filters like that and like that. And so he knows which part of the program and which level of decomposition he wants to override. And so he can examine actually this sequence and see whether the sketch applied here or not. That seems like too much work, but you need to understand what happens currently in real life. All these programs, the target programs, are written by hand. And the programmers need to keep track of all this. And now we are getting rid of a lot of it. And freeing them from any details and providing correctness as well. Yeah, but the issues of how to best tell the programmer of whether the sketch applied and why it didn't when it didn't, we don't have satisfactory answers yet.
Can I think of sketches as being somewhat like old-fashioned compiler hints, like the register keyword in C or the inline keyword in C++, where I kind of know what the compiler is going to do when it compiles the code, and so I give it a hint at a particular point that this local should be a register or this.
No, you shouldn't think of it as a hint, except as a strong hint in the sense that you need to follow that sketch. the compiler cannot ignore it. So the way to think of the sketch is as a non-deterministic program. Right? So what's going on here is we have one program that is simple but not very efficient. And then we have another program that is behaviorally identical but structurally very different. And it's a pain to write it. So what I do, I write a program that is non-deterministic in the sense that it encodes many possible executions. And one of them, or more than one of them, corresponds to the behavior that I started with, the one in the spec. And the fact that I can make it non-deterministic means that I can eliminate many details that choose a particular execution. And this non-determinism is removed by sketch resolution. So the best way to think of sketch is as we have one program, simple, slow, it's your behavioral spec, another one that rewrites it, but doesn't provide all the details, and you sort of complete it to behave like that, but be implemented faster, structurally slightly different. But we don't have an implementation yet that actually can resolve a sketch that is written as a non-deterministic program. Currently, these sketches are written as sort of rewrite rules. We will see soon how they will go. So the sketch is not very different than what we had before, except it encodes a space of programs. And out of those, we choose one that is identical to the one that we are rewriting. Now, how is this done? It's very simple because we come here to a filter whose behavior is indicated here. And now we resolve it such that we obtain this program, which is not non-deterministic, and we replace it here. Now, semantically, it's all done using matrix algebra. All these filters are represented as matrices. And so the decomposition of this filter into a pipeline of multiple filters is matrix factorization. So when these three matrices multiply to be this matrix, we have guaranteed correctness of this decomposition, which sort of guarantees our property that we don't introduce bugs. Now, what does the sketch do? The sketch introduces some constraints that these factors, these three matrices, which are these three steps, must follow. In this case, we say that this first factor must shift bits from 1 to 16 either by 0 or by 1 bit, and similar for the other two factors. So the resolution of the sketch is searching for a matrix decomposition that gives us this and also satisfies the constraints on these factors.
I have a question. That vector on the left-hand side, is it size node?
Yes.
So it's like 32 or 64 or something like
That's
that?
right. So this comes from the specification of the program, perhaps after some of those rewrite rules that were naively done by the compiler.
So, for example, I need to specify the length of that vector to use your system, right? For example, can I say that I don't know the length is a parameter, and can we still use your system?
Not currently. I think at least in the cipher domain, these block sizes and the sizes of permutations are fixed, so it's not a problem.
I see. And you expect it to be a power of 2? Are there those kind of restrictions?
No. No. But it may be possible to extend it such that these restrictions don't apply, but then you probably need a different algebra of rewrite rules.
So one thing is a little unintuitive. So if M is this matrix that can be decomposed into M1, 2, 3, ideally I would actually want to just do one matrix multiplication with M rather than 3 with these factor matrices, right? From an optimization point of view, right? The only reason you want to do the decomposition is because you can actually implement the simpler ones with an instruction rather than having to have an actual matrix and do the multiplication, right? Is that
well
how we should think about it? Because if these are general matrices that you can't replace with an instruction, but you have to actually do a matrix multiplication, then I'd rather want to use M rather than 3 individual ones, right?
True, but the reason why you decompose them is that by decomposing these matrices, you are really providing higher level steps of the algorithm.
So if I give you these decompositions, they're useless unless each individual step in the decomposition can be implemented with a simple instruction in your target architecture, rather than a general
that's not quite
matrix
true.
No?
These steps into which I'm decomposing a program doesn't itself need to be implementable with a machine instruction, and it typically isn't.
Okay.
These are not directly implementable with a single instruction. They need like 3 instructions.
Okay.
But usually when you do a decomposition, then each of these factors or filters in the pipeline that you created will be then decomposed further with other sketches, or perhaps just with the baseline compiler with the default sequence of rewrite rules.
Sure.
So the way to think about it is that this is sort of the algorithm you need to implement. And to do it well, you need to think of some higher-level steps of how to proceed. And here is one decomposition into higher-level steps, which seems to be working really well because it gets a lot of bit-level parallelism.
Right, I'm just asking about sort of the intuition, right? I mean, it's not clear that you're going to gain anything, right? It's not clear at all, right? Because if I can do the operation with one matrix multiplier, which has a square algorithm, right?
Okay, so I think here is I understand now. So the confusion is here. You are not actually using any matrix multiplication to perform these operations. Matrix multiplication is only the semantics for these bit permutations. Sort of, this is our vehicle for deciding how to actually decompose a given permutation into smaller steps. No matrix multiplication will actually be ever performed. So if I know I want to decompose it into 3 steps that should look like that, I can use the matrix multiplication algebra to decide what these steps should look like if they also need to have these properties.
Sure, but I mean, your search for the program, right? Your decomposition in the baseline compiler, right? Eventually, we'll have to emit some instructions, right? I mean, unless it finds some smart things because the matrices have some simple form, it will have to emit instructions that essentially have the same complexity as the original matrix multiplier, right? I mean, there's no magic, right? I mean, you have to do that, right? Mm-hmm. And so, clearly, if your decomposition that you're providing is not going to lead to simple instructions, you will have a 3 times complexity now. Well, it's a concept, but still, I mean, you're looking for efficient algorithms, and you're worried about.
Okay, so to answer that question, if you look at what the baseline compiler would do with its default rules on decomposing this matrix into lower-level instruction, you would obtain that slow algorithm, which you may remember on the side, that was linear in the size of the word, which was shifting 2 bits by 2 bits. So if you use that approach, that algorithm doesn't have access to the high-level view of the decomposition which the programmer has, and it will do something naive. So it will actually have more steps than here, linear in size of the word logarithm. Let's take it.
All I'm guessing is I'm just wondering about how do I, as a programmer, I don't really have any good intuition as to whether my decomposition is going to help or not, right?
Well,
it seems that I'm actually making the problem more complicated for the compiler.
Exactly. So that's why it's very non-local optimization,
that's
right?
What I'm asking.
And so the sketches don't help you gain that intuition except iterating faster through the process by rapid prototyping and the guarantee that you don't introduce any bugs, right? The system won't magically give you the intuition. It's just a tool for programming faster. Exactly.
So do you give any feedback on how the new implementation is better, or should I compile it and run it and see?
Currently, we just compile it and run it, but you can envision actually counting the number of instructions or cycles. That's sort of a less interesting problem that we didn't have.
So what exactly is the meaning of the sketch? I'm trying to figure out what my vocabulary in the sketch space is. Right? This says, first, so clearly you've got follow the arrow or don't follow the arrow, right? So you get 0 or 2, 0 or 4, 0 or 8. Can I also do things like in the same line, say you could do 2s or 0s or 4s?
In a single step?
Right.
Yes, you could.
So can you kind of tell us what the overall vocabulary there is for sketches?
Yeah, so in the current implementation, the vocabulary is that you can specify whether the bits should move by some predetermined set of constant positions. Okay. Or you can say that all bits need to, so that's one option. Another option is all bits in that word need to move by the same amount. But again, you don't determine what that amount is. So this is a different sort of constraint. And then there are two others which I forget, which is sort of simpler version of the two. So you constrain in various ways how bits can shift, and which bits will shift, and which of them will stay put.
I see. So then there's this built-in meaning in some of them that you have the option of shifting or not.
But the vocabulary you should think of as a particular constraint on the current system, that sort of version 0 prototype. You should really think of the sketch as a non-deterministic program that can follow various executions depending on some conditions that are like star conditions in non-deterministic
Right, but it's got some limits in it.
Some limitations, but some it doesn't. And so that's sort of the vocabulary for the sketch. That think of the sketch as a program that can take various executions. And the problem of resolving the sketch is one of finding an execution that implements the thing on the left.
So, is it that you use Boolean matrix algebra to resolve any sketch?
No. We use them to resolve these sketches which are most useful, these decomposition sketches, which take a filter, decompose it into a pipeline.
So just a quick question, what exactly does this matrix M mean over here?
The matrix M is an internal representation in the compiler of this filter, of this bit permutation.
So this whole thing about matrix factorization is very specific to this kind of a filter setup, right? It's
to this particular domain, and to the particular sketch where you take a filter and break it down into a pipeline of stages.
Okay, so in this domain you say that that is true, that is, you know, if you have a decomposition which is a matrix factor.
That's right. So in other domains the algebra may be very different, and we don't know yet what it should look like. But there have been a lot of work on optimizing, parallelizing compilers which have similar algebras.
Decomposition of the sketch follows the same path as the decomposition of the function that you want to implement?
In the sense that it falls into the baseline compilation process, and yes. So, so actually resolving the sketch is technically the most interesting part of the talk. But I think what is the most novel is the approach of finding a way of specifying what implementation we want. So to evaluate what we tried 4 experiments. The first, we wanted to see whether programmers can actually write these specifications, or called reference solutions, in the new language, in the StreamBit language. And we wanted to see how well the base compiler does, performance-wise, on these programs. Can they be compared with handwritten C? Then we saw how much sketching can help in improving the performance, and then compared our ciphers with hand-tuned, handwritten programs. So what we did, we took a bunch of programmers, have them develop a small cipher in C and in the StreamBit language, and measure the time it took them to do it. And so there are 4 programmers that finished in StreamBit and 5 that finished in C, and it took those programmers with StreamBit less time on average than those in C. Even though StreamBit is not the best language for writing those ciphers because they have unusual data flow structure, the paths cross, and that's quite hard to encode in StreamBit.
What was the total task here? So did they have to get a final program out and then run it and then be assured that it did the right thing?
Yes, and in the case of C programmers, which is the sort of second experiment, we allowed them to continue and tune the performance. So we come back here, we wanted to see what the performance was over time. So the StreamBit programmers developed the first version, they were done, and this is the time. And some C programmers continued and improved the performance in some cases significantly, but it was still almost 3 times less than the baseline compiler with no sketches did on our solutions from the StreamBit.
Do those StreamBit programmers have knowledge about what kind of sketches would be appropriate in that, for that problem?
They didn't, but they didn't do any sketching at this point, so that didn't hurt them. The only thing they were supposed to do is develop a working solution.
So they didn't recommend a sketch to be used in the
No, they didn't.
process?
The idea is that some other expert will come later and take their solutions and sketch a better implementation for them in a sort of decomposition between a domain expert, a crypto expert, and a performance expert.
All the C programmers, should they have knowledge?
They did get a sort of tutorial on what optimizations you may want to do on these ciphers, and some of them tried to implement them. But they were hard to do in a short amount of time because they required a lot of rewriting of the code. So then we took the worst of these implementations and did sketching on them. And see, in a time of over about 4 hours, the performance improved about 3 times. It was because you can very quickly write sketches and get feedback on performance and which of them actually work semantically and improve the performance. We had another guy, a C expert, implement the cipher now, taking as much time as he was able to bear and provide a good implementation in C. And he got up to here. So the sketched one is twice as fast and about 50% faster. And finally, we compared an implementation of DES with libDES, which is, we believe, the best publicly available portable DES version. And on 32-bit machine, we are about 17% slower in the worst case on Pentium 3. And we can overcome it when we make the sketching more general. And we were actually faster on 64-bit machines.
Yes. So how long did it take to develop your implementation, your reporting numbers for you?
Once the spec was done, I think it was 1 afternoon. So in 1 afternoon, Armando did develop maybe 6 different implementations by doing 6 different sets of sketches. So it was very quick compared to libDES, which is several years of effort with many people contributing ideas on how to do it. He, of course, stole the ideas on how to optimize from them, but he implemented them much faster. So what I have shown you with sketching in this domain, you have separation of aspects, the correctness and performance, and also separation of roles. You can have domain experts, like crypto experts, write the spec, and then somebody else come and actually provide an implementation without breaking correctness. And also, it's good to think why it worked in this domain. There is a big gap between how concisely you can write a cipher and what the implementation actually looks like. And we could come up with simple algebra of transformations that made it all possible. It's still open of how should the sketched program look like and what the feedback to the programmer should be. But I think as a concept, it's a very strong proof that you can iterate very quickly and get good solutions because correctness is guaranteed. And there are other domains where these properties, I think, are satisfied. In scientific kernels, media codecs, graphics, and somewhere else as well.
In a domain where the problem is so well understood that you know what particular operations are going on, how does this help?
So what do you mean exactly?
So if you knew all the sketches that are going into the program and you can code it efficiently, how does using a sketch help?
So there are domains where perhaps all the conditions are satisfied, but good implementation exists, like FFTs. Perhaps there is no need for a system like that. But as you start porting even in those domains to new machines like the multi-cores, you may consider building such a system because it's faster than building an optimizer or parallelizing compiler, because you don't need to train the optimizer to do all the standard transformations. You have just a set of rewrite rules, a way of sketching, and the programmers can sort of describe what implementation they want. So it's sort of a very quick way of writing and optimizing, parallelizing compiler, if you will, for a DSL. But yes, some domains perhaps are solved, and they don't need to be revisited. So at this point, it's perhaps good to philosophize a little bit and talk about the large implementation gap. And it seems that the large gap exists only between this sort of scientific high throughput programs where performance is important. But if you step back, you actually realize that the implementation gap is something that goes through algorithmic research all around, right? Most research in algorithms is about obtaining better performance to standard problems. So could you claim that a binary search tree, a standard one, is a specification of a red-black tree, which you could sketch? And so if you think about it that way, perhaps we could use sketching in areas that you wouldn't consider high-performance areas and just write a simple program that is executable, but is so simple that you trust it as a specification. It's executable, you can debug it. It doesn't use logic, so perhaps it's accessible to programmers. And then sketch the implementation that sort of improves of it. You sketch rotation by showing how just one link rotates. And the synthesizer will finish the code that implements the red-black tree. Skeptical?
Very good idea. But the red-black tree example that you gave right now,
Wasn't that a similar problem that the people in Settle tried?
I don't know.
They tried this automatic data structure selection.
Maybe they tried, but see, if they did, it's just a proof that maybe an argument for why you need to actually sketch. Because we don't rely on being fully automatic. We let the programmer specify the hard things and synthesizer to fill in the details that guarantee correctness. So sort of programmer-synthesizer symbiosis. Whether we can pull it off for the pointer-based code is not clear, but I would claim there is an implementation gap as well.
So did you ever end up with any sketches that were worse than the base compiler?
I don't know. I would have to ask Armando. So, but what if there is no implementation gap? What if the spec here and the code are pretty much at the same level of abstraction? What if the spec is hard to write? What if there is no rewrite algebra that you know of? Can we still use the idea here? And what I'll tell you about next, very briefly, is a system where we don't provide any spec a priori. We just sketch the desired implementation. We generate multiple versions of the completed sketch. And then the programmer looking at these codes will select the desired one, sort of selecting the specification after the synthesis. This is in cases where the specification is hard to write. So Sriram is cringing, so I'll try to convince him there is a reason for doing this.
I just don't understand what it is.
So the thing is that you sketch the code that you want to obtain, but you don't specify the behavior it should have. You synthesize several candidates, and by looking at the code, you realize, oh, I know I want this one. It does have the behavior I want. So the problem here is help with reuse, right? So the reuse has been known to be great. People wanted to do more until Lamson said, well, good luck with that, and said there are really just 3 reusable components. They have a lot of functionality under the simple interface. And the rest of the components may be hard to sell, compose, and understand. But recently, the first 2 problems have been solved, almost. It seems to pay to give components away for free. Design patterns provide connectors for components, but they are still hard to understand, these components, because in order to make a flexible set of components, you need to have small Lego pieces. Because they are small, there will be many of them. So in practice, it looks like this. In Eclipse 2.1, I knew there was an Java parser because somebody else used it. So I found a handle to the Java file of type ifile. I found a type for the AST node, and I thought in a few minutes I will be able to invoke the parser and get the AST for the code. It took 2 hours. And the reason why it took so much is that it's actually a very hard task. I asked my students to do it. Actually, they ran into the problem independently. It also took them 2 hours. So I felt better about myself, but I felt worse about the reuse. And the reasons why it's so hard is that if you follow expected designs, you're not going to find the code because you expect 1 level of file handles. There are 2, these 2 red types. You cannot use class browsers because there are 2 classes you don't know about. And if you then resort to grep, you're not going to find anything because the method that you need here, parse compilation unit, returns compilation unit type, which is a subclass of AST node. So if you are grepping for that, you are not going to find this either. So this is actually a good design and convinces us that in other APIs, we'll face similar problems. So we decided to sort of attack the problem since it's not going to go away. And the idea is to have the programmer express the programming intent, and the system will supply the code that sort of implements the desired reuse. But the problem we faced was the programmer often doesn't know exactly how to say what he wants to do. Often his intent is as vague as parse my file. So to face that, we let the programmer state a partial intent. We synthesize multiple candidate codes, and then the programmer will need to select from among them. So it's sort of like the search engine experience where you just enter a few keywords, and then from the few candidates, you can quickly select what you intended to look for. And that's faster than actually making the specification of the keywords more precise. So sort of the burden shifts to post-mortem, post-search, or post-synthesis where the problem is easier. So we are ready for a problem statement here. And the problem is that we'll feed the synthesizer first some input that teaches about the API. And it will come first from API declarations and then from sample client code. I'll talk about it later in the second half of this fragment of the talk if there is time. And then once we teach it about the API, we can then ask the programmer for the intent and generate code that can be directly inserted into the code being written, and the candidates are ranked so that the programmer can select from them. So now that the problem is set up somewhat, we can show you 3 observations that make it all possible. The first one is somewhat surprising that most of these reuse problems can be specified with a simple query that is a pair of static types. The first one is have type, second is want type. And what the query says, I have a pointer to an object of some type, and give me the code that results in a pointer of the want type. So sort of generalized type conversion, if you will. So in our example, this is the have type. We have a pointer to this file, and we want to obtain a pointer to an AST node. And this query, however loose, is usually actually quite sufficient. Now, there is another observation about the code that we need to generate, and we call it a jungloid. And the jungloid is just a chain expression, a unary expression composed of unary expressions, which in the case of Java, field accesses, instant methods with 0 argument, static methods with 1 argument, and the conversion to a supertype. So here is our jungloid. It's a call to a static method with 1 argument and an instant method with, well, 2 arguments, but this is a non-pointer argument, which we simply ignore. Because these are easy to specify later once the code is synthesized. These are sort of configuration parameters. Now, if the code is not a jungloid that you desire, we still can help you. And in fact, this is the powerful mode of use of our generator. If this is the code you need, then so the data flow graph, there is a method with multiple arguments. Then it really has 2 jungloids here. And the user would first generate, say, this one, and leave a free variable. The synthesizer would leave a free variable, which you can then initialize with synthesizing in the second invocation of the synthesizer another jungloid. So we wanted to see how general actually this definition is. Does it cover interesting cases? So we picked 16 reuse problems, and 12 out of them could be described with the query. So it was pretty good, 3/4. And then out of these that are describable with the query, 9 had jungloids that were straight jungloids, and 3 of them required composition of multiple jungloids. So repeated invocation of the synthesizer. Now, once the problem is defined like that, how do we synthesize jungloids? And at this point, because we took care to state the problem in a very simple way, synthesis becomes trivial. We have a program representation where each node is a type, static class, class, that's so a static type. And it's connected with edges that represent these unit jungloids, so methods that convert one pointer to another or widening. Now, given a query which is a pair of types, such as ifile over there and AST node, each path between these 2 nodes is a jungloid. Now, the problem is, with so many jungloids, which of them do you actually offer to the programmer? It turns out that usually the shortest path is the desired jungloid that the user wants. So among the k shortest paths is the code that the programmer wants in like 90% of cases that we looked at. So now the probably most interesting part from the user point of view, how do we actually make the synthesizer available to the programmer? And the way we do it is put it into the code completion that's standard part of IDEs. And so what this happens in code completion, that if the cursor is here at this point, use the Java type system to determine which methods or fields are accessible on that variable file. And this is what an IDE would give you, a set of methods here with their help. So we sort of overload that. And if this is what the programmer has written so far, and invoke the synthesizer at this point, then we know that the want type is AST node, because we need a value that is of this type. So this is the want type. The have types come from the lexical scope. These are our 2 have types. And so having these 2 sets of types, actually the want type is always a singleton, we have these two queries, which we can then feed to synthesizer. And it will generate the candidates which we rank and offer to the programmer like this. So here is the various code that we synthesized. And actually, you see it contains nested methods. So in one line, nested methods here. And here they are broken into 2 lines for readability. So if you look at this and step back and think about the sketching equation, what is it that we have here? We have a partial implementation here which sort of acts as a sketch. And we are looking for ways to complete the program by synthesizing several candidates. And then the programmer, by seeing the candidates, can easily choose the right one. And it's actually true that the selection is easy, as I'll show you in a demo. And then selecting it. And choosing the right one effectively selects the desired specification. And I'll show you in a demo how the process works.
Ross, I have a question.
Yes.
So let's say that you want to get bar from foo. But it turns out that the correct way to do it is to first generate bass from foo somehow and then feed both of those to a method to generate bar. So this is, I think, the case when you need 2 things.
Yes.
How does so here you showed that you first come up with like, 1 pair queries, right? So how does the programmer realize that that is not enough, so he better try this thingy, this other method where you have to generate 2 things separately and then feed them together?
So I'll show you in a demo, but the idea is simple, that the programmer doesn't actually know what the have types are. He just wants to generate some code that provides the desired value. And some of those codes may be one that has the free variable, which means a method with multiple arguments. And he looks at this code and says, this is the code that I want, but there is a variable that I need to initialize later, and reinvokes the synthesizer again. So simply by looking at the codes that are good candidates, he will see, oh, I see, this is the code, but I will need some stuff later, so I'll reinvoke Prospector. I'll show you in a second.
So it seems almost trivial to extend the jungloid search for jungloid trees, or whatever you want to call them, where you would just do that nested querying yourself. Why was that not something you did?
It seemed trivial, but we've been on this path with Jim and Glenn in the past, where we tried to learn specifications that were not chains but trees. And then the shortest path heuristic, which is so important for ranking, breaks down. You sort of need to have the shortest hyperpath, and selecting them is so hard. So actually, one of the best things about the work is the decomposition, that the user much rather deals with a skeleton and says that, yes, this is what I need, and insert it, and then sort of build it up.
A lack for good heuristics, is it?
It's, I think, for the lack of good, yes.
Tree is just
heuristic is one thing, that we couldn't come up with a good one. Then just theoretical handling of the problem, that you are dealing not with paths but with trees. And then just programmer comprehension. It's harder to understand a code that is a tree than is a skeleton. But in principle, you're absolutely right. It could be extended, and maybe in some cases we'll extend it like that. If the confidence that this is the tree you need is then it's part.
So it seems like giving the programmer all these alternatives that are basically going to produce the right translation of types, but not necessarily the semantically correct thing that they hope for. It's just a recipe for introducing a lot of errors into code, because the actual sequence of conversions that you generate may never be a real sequence that anyone would want to do. It just happens to be something that's possible. Have you thought about trying to correlate the sequence to actual sample code? In other words, I mean, it'd be much easier for a programmer not to select one of these things from a pull-down menu, which are arbitrary in some sense, but to sort of be taken to a piece of sample code that does exactly what they want, so they can verify what's happening by looking at the code as opposed to just by looking at a signature. Have you thought about that?
We have thought about it, but after doing some experiments with real humans on real APIs, it turned out to be not necessary. And this is why I claim that after seeing the generated candidates that are over calls to the API, these candidate codes actually are like specifications. They're as concise as you may want. They are sort of in the language of the specification. And so just seeing the sequences often convinces you, often without going to documentation, yeah, this does what I need. So let me just show you. So what I have here, I have a file name here in a string, and I want to create a buffered reader. And I myself never remember how to do it. So you invoke Prospector, the control space, and it gives you these options here, ranked. And here is the same, except broken down into 2 lines rather than nested here. And I couldn't enlarge the font, so I apologize. But if you look at this, what do you see? That the first 2 are identical. You create buffered reader with a string reader, and it's the same except there is this one extra argument, which I don't know what it does. So you configure that later. You look at the next 2 lines, you create buffered reader out of a file reader. So immediately see that these 2, the contrast between these 2 lines actually determines the semantics of the string. It doesn't contain the content, but it contains the file name in this case. And you, as the programmer, see, oh, I want to open a file, not open a string. So you select the second. And it's inserted there. And you see that it would be much harder to specify that the string you have is a file compared to just selecting from these 2 options. And also by looking at these 2 options, I saw, yeah, this is exactly what I want. And now we could cross-validate it with sample code. But in some cases, it wasn't necessary. But yes, you would really need some sort of verifier that the intent is the same. But I would argue that this system should never go into this total soundness thing. It's sort of a synthesizer that the programmer eventually has a responsibility that it uses is the right way, perhaps by reading the documentation.
But that 0 kind of bothers me. It's like, do I choose the one with the 0 or not? And if I don't know what the 2 are, I mean, it's,
no.
It's like a flip a coin
today, right? By looking at these.
It just makes it easier to write code that's incorrect.
No, it doesn't actually. No. So I didn't argue that you shouldn't check what the 0 is. You should read the documentation and do it. But at this first level of approximation, you know that this is not what you need. And so, no, so you want to verify the thing as correct. But I don't think it would be by the standard verification. I think it should be done by better API design, in a sense that when these types match, right? How do we build jungloids? There is this. We just look for compatibility of Java types. Then the code is guaranteed to do the right thing. And sort of make the types richer that we would never plug in together the jungloids that do a wrong thing. And that can be done with precondition, postconditions, and the ideas would still apply, I think.
So I have a question. So I think, I could be wrong here, but that argument is probably the buffer size. So where did the 0 come from? When you have...
the 0 is the default value for an integer argument.
Okay, so you have a bunch of default values that you use.
Yeah, so the programmer needs to know that that 0 could be a wrong argument, yes.
Okay.
So do you, in your heuristics for ranking these things, do you take into account, let's say, that something is a reflection API? Because you can create always something from anything by perhaps changing it to string and then create based on the name, right? So there's always a two-step jungloid for any transformation, right?
So strings are currently excluded as intermediate types. No, they can be at the end, but not in the middle, because they are so overloaded, like objects. So now we have a solution which I probably won't talk about, which is very interesting, on how to refine types by doing mining of a corpus of a client code, which sort of gives types more precise meaning, sort of separating nodes in the graph, generating more precise jungloids. But the key heuristic is the length. And then some sort of secondary heuristics are, does the jungloid cross many packages? And if it does, you sort of give it lower weight. But the length seems to be the usual thing, which makes sense because you wouldn't design an API that takes too many steps to implement a straightforward task. But it's still a heuristic.
Back to a point you just made, because I think it's important, which is, we should think about this as more of the API design experience. So, right now, if I'm an API designer, how do I think about my job? Well, I think I'm basically putting this large bucket of functionality out there, and a document that says what each entry, so I give out this list of method signatures, right? And I give documentation for each one. And then maybe if I'm really good, I write a tutorial document that gives some more guided advice about how to use the thing, right? But, what sucks is that's both difficult to consume and it's difficult to produce. Like, nobody's happy with that. So, maybe this is a way forward, right? So what an API producer is supposed to do is provide this kind of guided jungloid experience So, what you're doing is you're designing not only the set of method signatures, but the set of kind of IntelliSense pop-up prompts that lead you through the API for, so I'm actually explicitly designing, this is the constructor I want almost everybody to call. If this isn't going to work for you, here's the next one or the next 2 or 3 that you might want to think about that have additional parameters. And I'll walk you through that experience of becoming more sophisticated.
So you're talking about better ranking of those candidates, and that's probably necessary, but I think what would be the first thing you would want to provide with an API that will sort of make this synthesizer more trustworthy? Better types in the sense of precondition, postconditions, to guarantee that whenever we synthesize a jungloid, it's guaranteed to work in a particular context. And
now my point is that if you read a tutorial document for an API, that is not how they're described, right? They don't say, first, think about your program state as a set of predicates. Then find the method whose precondition is actually callable from the set of predicates that's true in that program state, right? They're not written that way. They basically say, look, most of the time when you want to pop up a window, call this. If you, for some reason, need a transparent window, which is almost never, but if you do, call this other thing, right? It's a very guided kind of experience, and this jungloid gives you a way of making that more systematic and not so much based on text, like on websites or in documents or whatever. That was my point.
Yes. Well, one perhaps way to summarize it is that when you read documentation for APIs, it's usually centered by class. There's documentation for a class, but what jungloids show is that you actually want documentation for multiple classes at once. So the cross-section should go across classes rather than across methods in a class, because that's how you use them.
Did you know that this functionality was also provided by the Tipsy tool that developed at CERN?
Tipsy? No.
Okay. They didn't have the cool interface, though.
Mm-hmm. So they did such synthesis?
From having a from type and a one type.
Mm-hmm.
Christy Bolton and Greg Nelson. It's written up as part of a summer intern
tech reward collection.
Yeah, I'd like to know about that. One thing that is sort of technically more interesting is what I did not show you, and it's the problem with downcasts. So from the program analysis point of view, this is again the most novel part. That if you have, I'll just state the problem and let you think about how to solve it. But imagine you have a the jungloid that looks like that. You have a project out of which you want to get targets, sort of make targets, and then you want to, from the targets, get a target of a particular name. And since targets are hash tables, you need to do a downcast. Generics, by the way, don't solve the problem. Quantitatively, might be only 50%. So the problem with the solution here is that this is our graph built out of signatures. And you see there is no path from project to target because downcasts so far have not been our elementary jungloids. Now we could add them into the graph. But besides the jungloid that we want, we would also get this one, which is shorter. And it will throw a downcast exception. So how would you solve the problem? Well, what you really want, so this is the bad jungloid, is a graph like that where these types are refined. So we'll get a node for a hash table where the hash table is such that when you call get on it, it returns a target, an object with type target. And a type for object, so an object with static type object such that its dynamic type is a target. And then the downcast to target will succeed. So how do we create these refined types? I don't know of any work that would actually do it. So just quickly, the solution is look at the corpus of clients, client code over the API, and extend the graph that we obtain from signatures with these snippets. We call them example jungloids. So if the piece of code the client contains this sequence, which is these two calls originating from project ending with downcast, I will merge it into this graph. And now I obtain a jungloid that is legal, that won't throw an exception. So we sort of learn from the corpus of client code on how to use the downcasts. Now, there are, of course, issues here. How do we make this example jungloid that we extracted and added here not too long and not too short? Because one leads to incompleteness, the other one leads to a lack of soundness. So here is what happens when you get a larger one. You don't get this jungloid here, which is what we wanted. If you have a shorter one, you can synthesize jungloid that on any hash table will do a downcast to target, which is wrong again. So the solution is find the right context to extract. And so think of this here as client code, which contains this example in it and this example somewhere else. And we start from downcast and we start extracting longer and longer chains until each downcast, one downcast to property, downcast to target, is distinguished by a different context. So right now they are not distinguished. They are still not distinguished because they have the same context, the same sequence of calls. But if we extract a little bit more of context, now we see that this chain of calls is different than here. So we know that after this chain of calls in the corpus, we were able to do downcast to target, and similarly to property. And this is the minimal context that distinguishes them. So this is what we extract and add to the graph. And sort of can argue good properties in the sense that we would like to synthesize only jungloids that are correct, in the sense that once you synthesize them, you actually can write good client code around them, one that doesn't throw downcast exception. And we can achieve this ideal in the limit that is not so severe. Limit is infinitely large. That's hard to achieve, but there is a lot of client code out there. Bug-free corpus. Now, this seems severe, but the bug-free in this environment means client code in which, at least for some input, the API usage is correct. Because no client is correct for all inputs. But if there is one input on which there is a correct usage, we want to use it for synthesis. And just quickly, we looked at ranking. We can actually, in 90% of cases, find the desired jungloid in top 5 candidates. So the ranking works reasonably well. We can fix the other problems. Then we did a user study. We gave programmers 4 problems to solve, 2 with Prospector, 2 without, and measured the time it takes them to solve them. And on these 4 problems, typically Prospector led to code that was written twice as fast and was more correct too. Without Prospector, programmers often reused code, but by re-implementing. They found 100 lines of code and cut and pasted it. So it's a reuse, if you want to call it reuse. But often they made errors in the re-implement class. They had bad casts. Sometimes the code didn't compile. So Prospector always gave us the right solution. So there was an empirical argument, at least, for better correctness. There's some future work. But to summarize, so what I've shown you is sort of 2 ways of sketching. In the first case, there was an implementation gap, and the argument that this program here is sort of optimization of this program here, functionally identical, and you want to sketch how this should look like. In the second, we didn't know what the spec was, but by sketching the implementation, we got several versions, and by selecting the right one, we quickly could effectively select the specification as well. So there are other ways how you could use this equation to perhaps get from here with a spec into some outline, but that's work that's far out. So that's all I have. Thank you for your time.
Instead of having more questions, if you want to talk to Ras, you will be here for 3 days, so talk to Ras. Thank you.